Imagine you have 1,000 concurrent users and you have exactly one ticket left to sell. Now, if you let all 1,000 users hit your server at the exact same millisecond, your system is going to suffer from two fatal design flaws. First, the math breaks. A race condition might accidentally cause you to sell that single ticket to, say, 5 different people. Or second, your infrastructure breaks. The sudden spike in connections creates a thundering herd that crashes your server entirely. I've been wanting to make the jump into system design, and I figured the best way to learn was to build a project that intentionally breaks under that kind of heavy traffic. I'm James Mota, a software engineering intern and AWS cloud practitioner. To actually prove how this works out under load, I built a full stack implementation using a Spring Boot backend, a React frontend, and a MySQL database. Today, we are going to look at the why behind these failures, how database locking prevents the data corruption, and how introducing AWS SQS acts as a shock absorber to save the entire system. The link to the repo is in the description down below. Alright, let's jump in. Now, when it comes to actually selling one of these tickets, the logic seems pretty simple, right? I mean, first you would check if there is a ticket remaining, and then after that, you would be processing the card details that the user provided. You might say, check if the card is actually valid, and maybe you may call other API services or such. And finally, you would actually reduce the amount from their bank account, right? And once that's over, you would reduce the ticket from the database. But see, how will this actually work out when it comes to, say, 1,000 concurrent users? Let's have a look. So if you take a look at my order controller right here, as you can see in the post mapping, I have first made the order, and then after that I have got into checking the quantity of the product. So if the quantity is less than or equal to 0, we immediately fail the order. Otherwise, we move into a simulated order processing wait, which I have achieved using thread.sleep. So after this 20 millisecond delay, we will be decrementing the quantity from the product. So, I mean, in this code, it looks correct, right? This should work, right? But how does it actually fare against 1,000 concurrent users? So let's fire up a K6 script and let's see how it actually does under pressure. So to simulate this thundering herd, we can use a tool called K6. So K6 is actually a performance testing tool which we can use to, like I said, simulate the thundering herd. So let's have a look at my implementation. So what we are doing here is basically we are spinning up 1,000 virtual users and all of them will hit the endpoint exactly once. And in my function, or rather the function which each of these threads will run, will be the payload, the JSON payload. It will, of course, send this data to this particular endpoint, and to get an understanding of how many tickets were sold, I have done a check here, which kind of tells us how many tickets were bought, how many sold out, and whether if the system crashed for using a 500 error. So let's run the test and let's see what's going to happen. So upon startup, to actually populate this ticket, I have implemented a command line runner, which basically, when the app starts up, it will populate the database with this ticket row and it will give it a quantity of 100. So let's just check that first before we kind of run the load test. All right. Okay. So let's go to my workbench and let's have a look at whether if that was successful. And yeah, so as you can see, there are 100 tickets. So the whole test here is to check how 1,000 users do against one ticket, right? So let me just quickly make this one. Okay, apply. All right, so now there is one ticket. So let's jump into my K6 script. So here we are, and let's run this. It should work, right? I mean, the logic that we spoke of before, it should hold up, right? Let's have a look. Well, that was quite fast, wasn't it? So 5200 response, but there was only one ticket remaining. And what happened there? And what are all of these logs? Why does it say that this request has failed and connection couldn't be made? What's really going on here? Let's have a look. So let's quickly analyze the results that we got back. So first of all, if we look at this logs, we can see that so many requests have been failed. See, this is actually a problem with the operating system, where it basically has this thing called the TCP Backlog Queue. And what this backlog queue does is it kind of sets this limit for the number of connections that it can allow. So say, and by default it comes to around 128, I think. So but here, since we have populated it with 1000 at the same time, we are exhausting that backlog queue, and hence we are getting these network bounces. So getting into the actual source here, which is the fact that we oversold tickets by 49. So that is an example of a race condition, or more so specifically a flavor of race condition called the lost update problem. So let's have a look at what this lost update problem is and what's really going on. So to actually understand what's going on with race conditions, we need to take a look at the OS. So you see, when a request comes in, Tomcat actually assigns it a thread, and these threads are actually managed by your CPU's cores. Now, these cores are given a certain instruction by the OS scheduler to never actually be idle. So what does that actually mean for our context? So if you can see here, we have these two threads and both of their processors are very similar, right? I mean, both of them have check, process, and then act. But you see, because we have the processing here, which is 20 milliseconds, because of that processing, there is an IO block. So now when this IO block is detected by the thread, by the core which is handling this a certain thread, what it will do is it will save the state of that particular thread. The core will save the state of that particular thread, and then it will move on to another thread. So just think about it. Now, if you were to take this certain process, the only way you would know if the quantity has been decremented is once the actual decrementing has been done, right? So if both of these threads are both checking the database for the quantity at the same time, and because you have this OS scheduler also coming in, which does this certain IO blocking, the reads are stale. See, in thread 1, if we have a look at this, it checks the quantity from the database and then it pauses. So what happens there is the thread will, the core will stop the process there, and it will move on to another thread, saving the state. So the other thread will also read the quantity from the database, but it's stale data, because that thread too will be read as one ticket remaining. And this is exactly how the race condition issue actually comes into play. So just to simplify things, why don't we take a look at a quick analogy? See, now just take a cafe analogy, okay? And let's say you are a certain barista. Now let's say on a normal day where you don't have any restrictions, a customer comes in and a customer sees that there is a slice of cake and the customer wants this slice of cake. So what would you do? So of course you would take the order from the customer and then you would process his payment, whether be it cash or card. And then after that, you would give him the cake piece, right? So you would check if there is a cake piece, then you would process his payment, and then you would give him the cake piece. So so that is because you don't have any certain restrictions. But see, just think, one day your manager tells you that you can never be idle. You always have to move on to the next customer. So let's say on a certain day there are two customers coming in, and let's say one customer wants a certain slice. And what would you do? Okay, you would go and check if there's a slice, and then you would process the payment. But see, when you're processing this payment, you're not really doing anything, right? So because of this rule, you have to now take on the responsibility of checking out customer B's process. So how does customer B's process start? It starts by checking if there is a slice. So see, since you haven't actually decremented the quantity of the slice from the previous customer's order, when it comes to the customer that you are entertaining right now, the data is stale, right? Because you haven't actually done the reduction yet. And see, this is exactly what is going on in the OS. Because of the OS's feature of this rule where a core can't really be idle, because of that, race conditions are formed. So we just had a look at what this race condition is. So the question arises, how can we actually prevent this from happening, especially when there is a thundering herd? We will be looking at certain solutions which starts from optimistic locking, pessimistic locking, and atomic updates. And to solve the problem of thundering herd, we will be using AWS SQS as, like what I mentioned earlier, shock absorber